So if you've been following AI at all, you've probably seen these absolutely massive numbers flying around. 7 billion, 70 billion, 175 billion parameters. It's kind of confusing, right? It's really easy to just look at those and think, well, the biggest number must be the best one. But is that actually true? Let's get into it and figure out what these numbers really mean.
And that really is the million-dollar question we're going to tackle in this explainer. For a long time, the whole industry was basically in an arms race to build the biggest, most massive AI model they possibly could. But as you're about to see, the story has taken a really fascinating and, honestly, a pretty surprising turn. Okay, so first things first, Section 1, AI's billions of switches. Before we can start busting any myths, we gotta get on the same page about what a parameter actually is. You can think of them as the absolute fundamental building blocks of an AI's mind.
At its heart, a parameter is like a tiny, adjustable switch. But it's not just a simple on or off switch. It's a smart one. It holds a little piece of information it's learned, a tiny nugget of some pattern, and it uses that to help the AI make decisions. And modern AIs have billions, sometimes even trillions of these things.
This is a great way to picture how it all works. Imagine the AI's brain is just this colossal, unbelievably complex maze. When you ask it a question, a thought has to navigate through that maze to find the right answer. And at every single intersection, at every fork in the road, there's one of these smart switches, a parameter, guiding the way. One switch might have learned that the word Paris often comes after capital of France, so it flips to high priority and lets that thought go down the right path. This happens billions of times, all in the blink of an eye.
All right, on to Section 2, the case for more. So if parameters are kind of like an AI's brain cells, then it seems obvious, right? Having more of them has to be better. Well, for years, that was the logic, and honestly, it was a pretty compelling argument. Let's dig into why that race for size got so intense.
I love this analogy because it illustrates the difference in scale perfectly. A 7 billion parameter model, it's like a really smart student who's got the textbook memorized. Incredibly capable, great for most things you throw at it. But a 70 billion parameter model, well, that's more like a world-renowned professor with an entire library living inside their head. It doesn't just know the facts, it sees the deep, subtle connections between all of them.
And this is what all that extra scale gets you. Suddenly, the AI can grasp nuance, sarcasm, and subtext. It can hold a staggering amount of world knowledge in its memory, and it gets way better at abstract thinking. But the most exciting part, the thing that really drove the race, was the discovery of something called emergent abilities. Okay, this is one of the wildest concepts in all of AI. Researchers started noticing that once a model got big enough, once it crossed a certain size threshold, it would just spontaneously develop brand new skills. All of a sudden, a model that was only trained on language could do math problems, or write working computer code, or translate languages it was never specifically taught. It felt like magic, and it just poured gasoline on the fire that scaling up was the one true path to real intelligence. But here's where our story takes a crucial turn. Section 3, the myth of size. The industry was going full steam ahead, just building bigger and bigger and bigger models, assuming that intelligence would just scale right along with it. But then, the data started telling a very different story. Which brings us right back to our big question. After all that scaling, after all those incredible emergent abilities, is the relationship really that simple? Does adding more parameters get you a direct one-to-one increase in intelligence? And the answer, put as simply as possible, is no. And this, right here, is one of the most important shifts in understanding in the entire field of AI today. See, here's the crucial discovery. The returns diminish, and they diminish fast. The relationship is logarithmic, not linear. What that means is, to get just another small bump in performance, you might need to make the model 10 times or even 100 times bigger. All of a sudden, just making the models bigger started to look incredibly inefficient. Okay, so if size isn't the whole story, then what is? Well, that brings us to our fourth section, the 3 real keys that go way beyond just the parameter count. Researchers figured out there are 3 other variables that are arguably way more important than just that raw number. The first one, and maybe the most important factor of all, is the quality of the data the AI learns from. It turns out what you feed the machine matters a whole lot more than how big its brain is. You know the old saying, garbage in, garbage out. It's never been more true. And wow, this chart just says it all. Look at this. On the left, you've got Meta's Llama 3, a pretty small 8 billion parameter model. And on the right, the original GPT-3, an absolute monster at 175 billion parameters. But look at the performance bars. The tiny Llama 3 actually beats the giant. How is that possible? Because it was trained on super clean, pristine, textbook quality data, while the older, bigger model was trained on a much messier slice of the internet. Internet junk. The second key is training time, or put another way, how long the model actually gets to study the data. Think about it. You can have a massive brain, but if you only have 1 week to cram for a final exam, you're not going to do as well as someone with a smaller brain who's been studying that same material for a full year. This whole idea was proven by some critical research known as the chinchilla scaling laws. What they found was that for any given amount of computing power, you're better off training a smaller model for a longer time than a huge model for a shorter time. And it turns out a lot of those early giant models were actually seriously undertrained for their size. And that brings us to the final key, architecture. This is all about the cleverness of the model's design. It's not just about how many brain cells you have, it's about how you wire them together. So, on the left, you've got the old way, one giant monolithic brain. For every single task, no matter how simple, the entire brain had to light up and get to work. Super slow, super expensive. The new way, used by models like GPT-4, is called a mixture of experts. Instead of one giant brain, you have several smaller, specialized expert brains. So when you ask a coding question, only the coding expert brain activates. This gives you the power and knowledge of a massive model, but with the speed and efficiency of a much smaller one. It's really clever. So, what's the big takeaway from all this? Well, we've basically arrived at a new frontier. It's about getting smarter, not just bigger. The old brute force race for size is pretty much over, and a new, much more nuanced race has begun. This quote from our source material just sums it up perfectly. The new goal isn't just to add more brain cells, it's to make each brain cell and the whole network that connects them work as efficiently and as intelligently as possible.
So, the next time you see a headline about an AI model's parameter count, remember these 3 things. The real story isn't just about the size anymore. It's about the quality of its data, the duration of its training, and the brilliance of its architecture. That's the new trifecta of AI progress.
And that leaves us with one last really fascinating question to think about. That first wave of emergent abilities came from making the models bigger. So what incredible, unexpected new skills are going to pop up now that the focus has shifted to making them fundamentally smarter? That is the mystery we're all waiting to see unfold.